I've noticed a lot of young developers diving straight into microservices without fully understanding the implications. It's like they think it's just another buzzword.
Yeah, it can be overwhelming to see all these new architectures popping up. Sometimes you just want to stick with what you know works.
Absolutely. But sticking to the same old methods won't scale well in today's environment. You need design patterns that can handle rapid growth and changing demands. Take the service mesh concept, for example. It provides a way to manage network communications between services reliably.
True, especially when you have dozens or even hundreds of services talking to each other. Managing them all directly would be a nightmare.
Exactly. And then there's the idea of using event-driven architecture. By decoupling components and letting events trigger actions, you can build systems that are both responsive and resilient. But implementing this requires careful planning. Otherwise, you end up with an overly complex system.
I guess finding the right balance is key. Too simple, and you're stuck. Too complex, and you're drowning in your own spaghetti code.
Spaghetti code is definitely something we want to avoid at all costs. Another important aspect is ensuring your system supports horizontal scaling easily. That means designing stateless services whenever possible, so they can be replicated across multiple servers seamlessly.
Makes sense, especially since cloud providers make it so easy to spin up new instances. Just gotta watch out for those sticky session issues, though.
Sticky sessions can indeed become problematic, but by focusing on statelessness and consistent API contracts, you minimize such risks. Also, don't forget about caching strategies. Proper use of caches can drastically improve performance under heavy load.
Caching does wonders, especially when dealing with frequently accessed data that doesn't change often.
Definitely agree there. So basically, the key takeaway here is that while modern design patterns offer powerful tools for building scalable systems, they also require thoughtful consideration and implementation to avoid turning into a maintenance nightmare down the line. Speaking of thoughtful consideration, let's talk about the singleton pattern. It's a classic, but its usage in distributed systems can be tricky.
Oh, absolutely. The singleton pattern works great in single process applications, but as soon as you move to a distributed setup, things get complicated.
Exactly. In a distributed system, ensuring that only one instance exists across multiple nodes becomes a challenge. You need some kind of centralized coordination mechanism to manage that singleton instance.
Right, and if you don't have that coordination, you might end up with multiple instances of the singleton across different nodes.
Precisely. This can lead to inconsistencies and race conditions. One approach is to use a distributed lock manager or a central registry like etcd or Zookeeper to ensure that only one node holds the singleton instance.
That sounds like it could add quite a bit of complexity, though. Isn't there a risk of introducing bottlenecks?
There is certainly potential for bottlenecks, especially if the central registry becomes a point of contention. However, the trade-off is often necessary to maintain consistency and avoid having multiple singletons floating around in your distributed system. Moving on to another pattern, the observer pattern can also pose some interesting challenges in a microservices architecture.
Absolutely. Implementing Observer in a microservices setup isn't straightforward because services are loosely coupled and typically communicate asynchronously.
That's right. In a traditional setting, the observer pattern is fairly simple with direct method calls. But in microservices, you need to rely on messaging queues or event streams to notify observers.
Yes, using something like Kafka or RabbitMQ seems like it would be necessary to handle notifications between services.
Definitely. Using message brokers helps manage the asynchronous nature of communication, but it introduces additional complexity in terms of managing topics, subscriptions, and ensuring reliable delivery.
And not to mention the overhead of maintaining these brokers and handling potential delays in event propagation.
Exactly. Plus, there's the issue of scalability. As your number of services grows, so does the complexity of managing all these observer relationships. You have to carefully design how updates propagate through your system without causing performance bottlenecks.
It sounds like a lot to keep track of. Is there any best practice for simplifying this?
One approach is to define clear boundaries and responsibilities within your microservice. Each service should only subscribe to events that are relevant to its core functionality. This reduces unnecessary dependencies and makes the overall system more manageable. Speaking of managing complexities, integrating legacy systems into a modern microservices architecture can be quite challenging. That's where the adapter pattern comes in handy.
Absolutely. The adapter pattern is perfect for making old systems work with new ones without changing their internal structures.
Exactly. It acts as a bridge between the legacy system and the new components, translating the interfaces and behaviors to ensure compatibility.
And it must save a lot of time and effort compared to rewriting everything from scratch.
Definitely. Rewriting legacy systems can be risky and time-consuming. With adapters, you encapsulate the legacy logic behind a well-defined interface that fits nicely into your new architecture. This way, you can gradually phase out older systems as needed.
That makes sense. But how do you handle the performance impact? Legacy systems can be pretty slow.
Good point. When using adapters, it's crucial to optimize interactions with the legacy system. You might cache frequent requests or batch multiple operations together to reduce latency and improve overall performance.
Catching and batching sound like solid strategies to mitigate those performance hits.
They are. Additionally, monitoring the adapter's performance closely helps identify bottlenecks early on. You can then fine-tune the integration points to ensure smooth operation alongside your newer services. Another interesting pattern to discuss is the factory method. It's particularly useful when you need to create objects across different modules in a consistent way.
True, the factory method allows for flexibility in object creation without tightly coupling the module.
Exactly. By defining an interface for creating objects, but letting subclasses decide which class to instantiate, you can achieve better modularity and maintainability.
That makes sense, especially when you have multiple modules that need to interact with similar types of objects, but might vary slightly in implementation.
Absolutely. For example, imagine you have different modules handling various payment methods. Each module could use a factory method to create specific payment processors based on the type of transaction, while still adhering to a common interface.
That sounds like it would simplify the codebase significantly, especially as new payment methods are added over time.
Definitely. The factory method pattern not only encapsulates the creation logic, but also makes it easier to extend or modify individual parts of your system without affecting others. This is crucial for maintaining clean and scalable architecture.